Hey guys, welcome back. We got day 43. We're going to talk about kinetic molecular theory and gases today. All right, let's dive right on in. So, to define a gas, and you probably know this, you might not have written it this way, but I like this definition. I got this when I was a grad student at Michigan State. And gas is a state of matter in which atoms or molecules, particles, right, gas particles, have a great deal of space between them and are free to move relative to one another, right, lacking a definite shape or volume. Gas conform to those of its container. Gases are less dense than liquids and solids. They form solutions, homogeneous mixtures with one another in any proportion, right? So when we say less dense, what do we mean by less dense? So let's highlight some things here, right? They have a great deal of space between themselves, right? Free to move relative to one another. They lack a definite shape or volume, right? And when we talk about gases, right, when we talk about less dense, we got density, right? It's going to be grams per liter, right? Think about, water is 1 gram per 1 milliliter, right? And so gases are in grams per liter density. They're 1,000 times smaller-ish than like liquids and solids. All right. So let's first, when we think about gases, let's talk about how they move, all right? And how they do it. So there's, kinetic molecular theory, right? And this theory, which is important, by Boltzmann and Maxwell. They talk about how gases are, right? And a gas, right, to predict, because again, the whole point of this is to predict its behavior, predict its properties, be able to know what's going to happen if I have a gas in a container or whatnot. So gases compose particles that are separated by relatively large distances compared to their size. All right? So we're going to assume that the gas molecules are very far apart. Now, we don't, you move your hand up and down or left and right, right? You can feel the air, right? And it's like, well, it's everywhere on my hand. But to the particle size, it's still the particles are very far apart. Now, another thing is that we might not realize, gas molecules are in constant motion. It's very, very fast, right? And it's very, very random. And they just continually bounce, right? They continually collide. They bounce with each other. They collide the walls of the room, the container, wherever they're in. Now, one of the things that we assume is that the collisions are elastic. All right, that means that if it's going, kind of like if you had a tennis ball, you took a tennis ball and you threw it at a wall. How fast, you threw it at, say, 40 miles an hour at the wall, and it hits the wall, it comes back at you at 40 miles an hour. That would be an elastic collision. Now, the tennis ball is pretty good, but it doesn't conserve all that momentum. If it's going 40 miles an hour going into the wall, it doesn't come back at you 40 miles an hour, right? We know that. It loses some of that energy, right, into the wall as it turns around. We're saying gas molecules don't do that. They just hit and move. They don't collide with any loss of energy. Another assumption is that the attraction or repulsive forces are weak and ineffective, right? That's not actually 100% true, all right? And so we're going to divide something called the ideal gas. Their size, so an ideal gas, size equals 0, and their attraction equals 0, right? They don't have any attraction to themselves. Now, the next chapter after this one in most chem books, and ours included, all right, although we've already talked about this, right, is intermolecular forces. So we've already talked about intermolecular forces. A lot of textbooks, it's coming up. Ours, we already talked about it. And that's how molecules and compounds interact with each other, right? And so if you're polar, you're going to be very attracted to another polar compound. Well, that happens in the gases as well, right? And it does matter. But we're going to say, for our purposes, it's ineffective. Now, the kinetic energy of the gas molecules, the energy, right? K equals 1/2 mv squared. The kinetic energy depends upon and is proportional to the temperature in Kelvin, right? So the Kelvin temperature, the temperature is a measure of their kinetic energy, all right? Now, I always do this in the classroom, and so I ask, whose birthday's today? And very rarely does somebody raise their hand, right? Because we don't have that many students. However, if we were in a lecture hall, if I was in a lecture hall of 400 people, whose birthday of the day, odds are somebody's going to raise their hand, all right? Okay. In the classroom, I can even ask, whose birthday this month? I might get one. Sometimes I get none. In 400 people, what would I get? I'd get several hands. I get many hands whose birthday is today or in this month. And then imagine if you had a stadium full. You go to even 20,000 people whose birthday is today. You're going to have lots of people whose birthday is a month. Lots of people, right? There's always going to be people's birthday month and birthday day. All right? And so when you talk about a mole of gas is 6 times 10 to the 23rd particles, right? There's a huge amount, right? So that law of averages, no matter what, you just got so many gas molecules. You have the whole bell curve and all that, mathematics going on. And so we have these speeds, a range of speeds, and because of that, all right, we can predict their behavior because of how many, right? It's just like if I look out my office window, next to not too far down the street is a McDonald's, and then across the street is a Dunkin' Donuts. And those two companies, I haven't gone to those two places in a long time. I have gone to them both, but not in a long time. However, they know with the law of averages how many people are going to go each morning. And they know how many people are going to come each afternoon. Right? It's not a surprise, right? They know on an average Thursday how many customers they're going to get. Right? It's the same thing we can do here with gases and their speeds. Right? Because some are moving faster and some are moving slower. Right? The mean square speed is the average speed squared for all the particles in the sample. And that's what we're going to use a lot. All right? And I'll use blue. All right? So the root mean squared, all right, speed. All right, so let's look at this. The kinetic energy is equal to 1/2 the mass times u, the root mean square speed, all right, which is u squared, all right? That's the average kinetic energy of one particle. So for 1 mole, you'd have Avogadro's number, right, multiplied by 1/2 mu squared, right? Because mass, all right, and that would equal Ke. All right. Now, this derivation right here, Ke equals 3/2 RT. That's we did that it's in my physical chemistry book, so it's a 300 level course. All right. We know that Avogadro's number times the mass is capital M. All right. And so when we get Ke equals Ke, we're going to get 1/2 the molar mass, the root mean square speed squared equals 3/2 RT. And so that u squared equals 3 RT over M. So the root mean square speed, is equal to the square root of 3 RT over the molar mass. All right. So that is what your book wants you to know. All right. The root mean square speed. Just helps us predict. So now, when we know that heavier molecules, all right, actually are slower at the same temperature because of the molar mass. And so this leads us to comparing speeds. All right, and so if I have the speed of particle number 1, and I have the speed, the root mean square speed of particle number 2, right? We know this ratio here is equal to the molar mass of compound 2 compared to molar mass compound 1. So if you had oxygen gas and methane gas, for example, right? Methane is smaller than oxygen, so right, in terms of molar mass, right? Because methane is 1605 grams per mole, oxygen's O2 is 32, right? So methane's about half as much mass as oxygen, so it's going to be going significantly faster than oxygen at the same temperature, right? And so, 2 words here with Graham. Graham came up with 2 words: diffusion. And diffusion is where we go and gases just go uniformly fill the space. So when gases move, if you introduce extra oxygen into a room, that oxygen goes and uniformly fills the space. It doesn't just go to one side area, right? It uniformly fills the space. Like if you're wearing like a body spray, right? If you try to just spray yourself down, some people will do that instead of actually, they just spray, right? That diffuses away from you, right? So it's stronger at the source, but as that scent goes and goes away. All right, that's diffusion. Effusion is when a gas goes through a small hole. All right, that happens all the time. Think about the helium balloons you buy. Right, happy birthday, congratulations, all that. Well, when that balloon, like after a while, the helium goes through the balloon, because helium is a very, very, it's the smallest particle we have, smallest element we have, right? Helium's small. And so it goes through that balloon, because that balloon's made out of molecules, and those molecules have space between them. So helium will fuse out, right? And so when we talk about diffusion and effusion, we can carry the rate of movement, right? The rate of movement, if we know one speed, we can do the other speed, right? So if you know what helium did here, you can figure out what hydrogen would do there, right? And just solve that equation. All right. So how do we measure how much gas is there? Is the next question we ask. And that's pressure. Pressure is how we measure how much gas is there, right? And so we know that molecules in a gas are in constant motion and they're colliding, right? And pressure is force over area, which is newtons per meter squared, which is a PA, a Pascal. However, we're going to use 1 atmosphere is 101,325 pascals. We're going to use atmospheres, because 1 is a much easier number to multiply and divide and all that than 101,325. Nothing wrong with 101,325, but we're just going to make it 1. Makes sense. All right. Now, there is something called standard temperature and pressure, and it's that, and we abbreviate standard temperature and pressure as STP. All right. Okay, now how is this measured? Torricelli came up with this, all right? And so a barometer, right, if you had a bowl of mercury, so this would be Hg down here. If you fill a tube and invert it, and you had mercury in there, the mercury would fall down to a certain amount. All right. So there's our mercury, and there's the surface of the mercury. So there's our mercury. All right. The pressure of the air, or the pressure of the atmosphere, either way you want to do it, that's pushing down on the surface of the mercury. Okay. This mercury right here That's, well, the top is a little bit higher, right, because of how the meniscus is, top of the meniscus there, right? This mercury to the surface, right, that height, that's the pressure of the height of mercury. So the pressure of the mercury is equal to the pressure of the air, all right? So the mass of this mercury, right, the pressure of the height would be equal to the height, the density of mercury, and then gravity, all right? G is, of course, 9.8 meters per second squared. The height is how high it is, and D is the density. The density of mercury is like 13.6 grams per cubic centimeter. So there's a lot, it's there. And so that happens to be 76 centimeters, 760 millimeters, 76 torr, 1 atmosphere, right? Happens to also be 14.7 psi, because we use a lot of psi in this country, or 29.92 inches. All right? And these four are exact numbers. These are exact numbers. Now, another unit of pressure is bar, and bar is 10 to the 5th pascal, so they just make it 100,000 pascals instead of 101,325. So that's, bar is close to an atmosphere, but it's not quite. It's a little bit less. All right, and so that's how pressure is measured. With air pressure, it's pushing, the mercury column. You could do it with water, but you would need it 13.6 times bigger than 76 centimeters, so that's quite a bit bigger. All right, you can make a barometer at home. I wouldn't recommend it. Most of you guys have a device that'll tell you from the weather station. All right, so that is how pressure is measured, right? All the air is pushing down in this again, right? And then this mercury column right here, that mass in there, all that mass is also pushing down, and those equal each other. All right, so that's how we do it. Now, some scientists, 4 of them we're going to talk about, has discovered some relationships with gases. All right, Avogadro. Right? When you think of Avogadro, what do you think of? I think of the mole guy, right? He's the mole. He's the particles. Volume is proportional to the number of moles. That's real quick, all right? Boyle, pressure times volume is constant. Charles, volume is directly proportional to temperature. And Dalton, right, is the pressure total is equal to the sum of the partial pressures. And we'll talk about that in a later video. All right. So first up, Avogadro. The volume occupied, right, by a gas, so the volume is directly proportional to the number of moles present at constant pressure and temperature. So we're going to get to the gas laws in a minute or so, a few minutes. And right now we're breaking down the individual pieces, how it was discovered. And there's conditions. So like if you look at a liquid, the liquid has a volume and a mass, right? And the density is temperature. It's dependent, but you have a volume, and that's volume of water. Like how much water do you drink? You could do a mass, but most of us do volume, right? And that's the variable we talk about. Mass. How big is, how much, if you're eating steak, or if you have whatever, how much do you lift weights with, right? That's a mass, and that's one variable. Gases have a few variables: pressure, temperature, and volume. And if those change, the whole thing can change. And so we got to keep constant pressure and temperature for this situation. All right? Now, this means that volume and volume, moles and moles. So if we had a 1 and a 2, 1 and a 2, right? That's what directly proportional means. So if the volume doubled, chances are the number of moles had to double, right? So if I go from 1 mole to 2 moles, I would go from however many liters, I'd double that liter, right? If I half the moles, I'd half the volume. That's what directly proportional means. Now, at STP, right, 1 mole of any gas, it should be ideal. We never write that out, but 1 mole of any ideal gas occupies 22.4 liters. All right, that's just what happens. It's 22.4 liters. Now, Boyle's law, pressure and volume are inversely proportional. PV, well, that would be PV again. And so, in this case, when one goes up, the other goes down. 1 and 2, 1 and 2, right? So if my pressure goes up, my volume went down. A balloon is a great example of this, right? If you have a balloon, you squeeze the balloon, right? You're reducing the volume in the balloon, the pressure is going up. So if you half the volume of the balloon, the pressure doubles, right? And you do that enough, the balloon's gonna pop and loud noise. All right? Now, but that's at constant temperature. Charles' law is volume and temperature, right? Volume is directly proportional to the temperature. So that's another one set up this way. I have B and I have T. All right? And so we have 1, 1, 2, 2. So at constant pressure, the volume of gas is directly proportional to the absolute temperature, not Celsius. So Celsius does not work here, right? Because if we would have 0 degrees Celsius to 1 degree Celsius, that would be an infinite increase in temperature, which means the volume would infinitely increase, which would be horrible, especially for your car tires if it went from 0 degrees Celsius to 1 degree Celsius, which happens on this planet in a lot of places. We don't want that. But really, it's going from 273 to 373. All right? 273 to 274. Ooh, there we go. That's better. That's 1 Kelvin, not a big deal. However, this is why your tires do change if it's like 80 degrees Fahrenheit out and it goes down to like 50 degrees Fahrenheit out. Like, oh, my tires are low because this happened. All right? Now, we are going to take these two and combine them. All right? We're going to have the combined gas law. All right? So we're going to have P1 and P2. We're going to have V1 and V2. And we're going to have T1 and T2. All right? And so this only works with constant moles. So N is constant. All right? Pressure. The pressure units. Now this is very, very important. All right? P1 has to equal P2. And it can work. So it can be in millimeters of mercury. It can be in atmospheres. It can be in PSI. It can be in bar. It does not matter. Right? Because if I go from 1 atmosphere to 2 atmospheres, that's the same thing going from 760 millimeters of mercury to, what is that, 152 millimeters, or 1,452 millimeters of mercury. Right? It works. Volume, same thing. V1 has to equal V2. Any, as long as they're the same. They have to be the same. Right? They have to be the same unit. So I can do liters and liters, milliliters, milliliters, gallons and gallons, all fine. Cubic meters and cubic meters, good. I can't do liters and gallons. That's not going to work. I can't even do liters and milliliters. I have to make them the same. Temperature has to be in Kelvin. And the reason it has to be in Kelvin because we can't have 0 on the bottom. It's an absolute temperature. All right. And these, again, these are ideal gases, where size is 0, attraction is 0, and collisions are elastic. The next law is the ideal gas law, where we have P, V equals N, R, and T. And so the pressure, of course, P is pressure. And then now it has to be in atmospheres, right? Because we are going to be using this R for gas laws. Right? So both of these R's are the same R. Okay? Both R's are the same. There's a liters, atmospheres to joules conversion. So they're the same gas constant. 0.08206 is the same number as 8.3145. That's just the units are different. We need this one because our volume needs to be in liters. Obviously our moles. And our temperature is in Kelvin. All right? So that's how the ideal gas law works. So now when the moles change, it works out. And if you look, it's kind of neat. If I divide by T on both sides, PV over T equals NR, right? Well, if I have 1, 1, 1, and I have P2, V2 over T2 equals NR, you see how they can be the same? They can equal each other as long as N and R don't change. That's how that we can combine the gas law. It's kind of neat. All right. Now, last one, to derive the density of a gas. All right. Density of a gas, we have PV equals nRT, right? Well, we know M is mass, all right? Molar mass, volume, density. All right. So what mass, if I take the molar mass, which will be M, divided by the mass, so molar mass divided by the mass, grams per mole divided by grams, would equal mole, correct? That makes sense? I did that backwards, didn't I? I said it correctly, but I did that backwards. Let's try that again. The mass divided by the molar mass is moles. Grams divided by grams per mole is mole. There we go. So if I put M in here, right, M divided by the molar mass, that's the number of moles, right? That is the number of moles right here. That's N, mass divided by the molar mass. So that gives me P, V equals mass divided by molar mass, moles, R, and T. Now, I don't like M on the bottom. So we have pressure, volume, molar mass equals mass, R, and T. All right. If I divide both sides by V, I would have pressure, molar mass equals mass divided by volume, R, and T. Well, what is mass divided by volume? Density. So that means I'm going to divide both sides by RT. That means I get pressure, molar mass, divided by R and T, right, equals mass over volume, which is density. So that is my formula. Density would equal PM over RT. Are you going to have to derive this? No. I just did it for you guys. RT. So the density of a gas, right? Pressure, the molar mass, and temperature. So as long as the pressure and temperature are the same, like if you're talking about in a room, the heavier the gas, right? As this number gets bigger, this number gets bigger. So the heavier the gas, the more dense it is. And so if you think about air, air is mostly nitrogen at 28, and then oxygen at 32, right? And then 1% argon at 40, right? So you're looking between 28 and 32, but around, let's just say close to 29, 30 grams per mole. So anything less than 28 grams per mole is going to float in nitrogen. Anything heavier than 28 grams per mole is going to sink. Right? That's even oxygen is a little bit more dense than nitrogen. Not much, but a little bit more, so it's going to be towards the bottom, which those of us who live on the ground appreciate that breathe oxygen. Right? And so things that are really, really heavy, like chlorine gas, weighs 70.9, that goes to the bottom. Things that are helium, like light like helium, like that weighs 4, floats to the top. Right? So that is how density of a gas works. All right, so in the next video, we're going to do some gas law calculations. If you have any questions, feel free to reach out. Otherwise, we'll take care. See you next time, guys. Bye.